to look at a specific sequence. This sequence is defined explicitly with the formula a sub n equal to r to the nth power. Now, depending on the r's value, we'll know whether that sequence converges or diverges, and whether it converges or diverges monotonically or oscillates. Okay, I want to look at the first one here, where the r is equal to 0.75. Now, what's happening here? The a sub 1, if you put in n equal 1, it'll be 0.75. A sub 2 is 0.75 squared. A sub 3 is 0.75 cubed. If you look at those values and just continue multiplying by 0.75 to get the next term, what's happening with this graph is that it's getting closer and closer to 0. So it's converging to 0 monotonically, meaning it's going in one direction. Okay, and in this case, the r is positive, and it's something smaller than 1. Okay, now in the second one, it's very similar to the first one, except now our r is actually a negative number. So our first term will be the negative 0.75, and then the negative 0.75 squared is actually going to be positive, and then cubed. What's happening here is that the sequence is oscillating. Flip-flopping back and forth, positive to negative, but because we're multiplying by 0.7, we're taking 3/4 of the number value each time. Those numbers are still getting smaller and smaller and converging to 0. So if you look at the graph, you can see that it does converge to 0, but it does it by oscillating. Okay, and now that situation was where we had an r that was negative. So it's below 0, but it is still bigger than negative 1. Okay, now in the third one here, we have an equation where the r is 1.15. So your a1 is 1.15. Your a2 would be 1.15 squared. Now what happens is you take a number that's bigger than 1 and continue to multiply by that number. Well, you're starting off with 1.15, and as you multiply each following term by 1.15, you're making it a little bit larger than it was the time before. So what's happening here is that this sequence is diverging because those numbers are going to continue to grow if you keep multiplying by 1.15. And it's diverging monotonically. It's going in one direction. And this is a situation where the r is actually bigger than 1. Okay, and the next one, we have that the r is a negative 1.15. So not only are we taking the absolute value of the number before it and multiplying it by 1.15 and making it larger in quantity, we have this oscillation going on. So we're going to have every other term is positive or negative depending on whether the n is an even or an odd number. So we're going to start with this negative 1.15, and then we're going to have a positive number a little larger, and then another negative a little bit bigger than that. And so each time these values are getting further and further away from 0 because they're being multiplied by 1.15, and it's oscillating, flip-flopping back and forth from positive to negative. So this one we'd say is diverging, and it's oscillating. And in this case, the r is actually less than negative 1. Okay, now the size of the r matters and the sign. In summarizing that information in this table, I've got that if you have a geometric sequence, that's a sequence that's in the form a sub n equal to r sub n, r to the nth power. This sequence, talking about the individual numbers, will converge to 0. Now I'm taking the limit as n goes to infinity. That's finding what those terms are getting closer and closer to. So that limit is 0 if the absolute value of the r is less than 1. So that's as long as the r is between negative 1 and 1. So it will converge to 0 because each time you're multiplying by something less than 1. So you're taking a fraction of what you had before. And it doesn't matter whether it's positive or negative. The negative just means it's going to be oscillating going towards 0. If the r was 1, So if your function were a sub n equal to 1 to the n, well, a sub 1 then would be 1, a2 would be 1, a3 would be 1, and so on. So that the sequence elements, a1, a2, a3, do converge to 1. So the limit of a sub n in this case would be equal to 1. So in this case, we would say that the sequence converges to the number 1, and that's when the r is equal to 1. Okay, now the times that this limit did not exist were when it was diverging. That's where the limit does not exist because it's growing and growing, and it could either be oscillating or not oscillating, but the key here is that the r is either less than or equal to -1 or bigger than 1. So looking at the number line here, when the r is bigger than 1 from here, just bigger, strictly bigger, so that means not counting the 1, here it's going to be divergent, and over here it's going to be divergent. It will converge in the middle here. This is looking at the specific r value, and when the r is 1, we also will be convergent because of this situation of the n's going to 1. Now let me look at the case where the r was -1. If you had a sub n equal to -1 to the nth power, well, the first term is going to be -1, the second term will be 1, the third term will be -1. So what you're having in this graph is you're going to have it flip-flop back and forth from 1 to -1, so it's not going to be convergent because there's not a unique value that those values are getting close to. So that's why at r equal 1 it still converges, but not at r equal -1. Okay, so now know these values because you need to be able to look at a geometric sequence and say, based on what the r value is, whether that sequence converges or not. It will converge as long as the r is between -1 and 1 or equal to 1, but it will diverge for the other values. Now, if the r is positive, you say that it either converges or diverges monotonically. That means it'll stay in the same sign. If r is less than 0, that's where we had that oscillation. So we'll either converge or diverge by oscillation.